into some more detail about. Towards the end, they implemented emergency plan changes and conducted emergency exercises that we observed and interacted with. We did a tabletop with Honeywell and the state of Illinois and our local officials here to make sure that we all understood our roles and responsibilities. And we walked away from all those activities with a clear understanding that this facility can be operated safely for reasonable seismic events and reasonable tornado events. This facility is safe. So I'm going to turn over our presentation to Brita, who's going to talk about the technical evaluation. Mike Norris is going to talk about our emergency plan. And Jim Hickey, who's going to talk about our inspection program. And then I'll come back up and talk a little bit more. Brita?
Good evening. Good evening and welcome to everybody who's here tonight. As Tony mentioned, I'm Brita Riley. I'm a project manager at the NRC, and I work on our Office of Nuclear Material Safety and Safeguards. My job at the NRC is to lead teams of our experts in reviewing licensee actions. And in this case, we reviewed Honeywell's safety basis and corrective action plan for seismic and tornado hazards. So tonight what I wanted to do is share a little bit about our process for conducting the review and the findings from our technical evaluation report. The NRC reviews licensees' actions to ensure that they meet the NRC regulations and protect health and safety. Our review is independent. We are not an advocate for any of the facilities that we regulate. So we conducted an independent review of Honeywell's proposed modifications to protect against seismic and tornado missile events. NRC employs many people with different specialized expertise. So one of my roles as a project manager is to put together a team of people to review our licensee submittals. In this case, we put together a team of experts that consisted of structural engineering, seismic hazards, chemical engineering, risk assessment, electrical engineering, and emergency preparedness. We use in-house expertise as well as some contract support. Typically, when we conduct our reviews, we use standard review plans which provide guidance on what NRC finds acceptable in terms of meeting our regulations. In this case, we use what we refer to as New Reg 1520, which is guidance for fuel cycle facilities. In November, Honeywell submitted its safety basis and corrective action plan to us, and it addressed protecting against seismic and tornado hazards. The team reviewed the submittal and found that it had enough information to begin a more detailed technical review. But during our review process, we identified questions and additional information that we needed, and we use a formal process to request that information from our licensees. So we issued a request for additional information to Honeywell, and they responded to that. Also, the NRC and Honeywell met and held conference calls to get clarification on information that the technical reviewers needed for their evaluation. And the NRC team also conducted several site tours to review the modifications as they were in progress, and they conducted reviews of calculations and procedures and other documents. The results of the team's activities are documented in our technical evaluation report, and that stands as the formal record of the team's activities. The technical evaluation report covers a number of different areas, including risk information, seismic activity in the Metropolis area, the design of structures, systems, and components, and modeling of chemical consequences. The TER also covers the emergency plan, but I'm not going to talk about the emergency plan tonight. Mike Norris will talk about that. So I'm going to talk about the first 4 bullets and our findings methodology that's similar to what many of our other licensees use, and we refer to that as an integrated safety analysis. The approach enables us to look at risk levels based on likelihood and consequences, and it is portrayed in a risk matrix. So I have a depiction of a risk matrix here. The risk matrix is made up of generally 3 categories of likelihood and 3 categories of consequences. So on the left hand of the matrix, you can see that we have low to high consequences as 3 categories, and then the 3 right-hand columns represent the likelihood of occurrence from highly unlikely to not unlikely. So the purpose of the risk matrix is to look at combinations of consequence and likelihood and determine the risk level and whether it's an acceptable level or not acceptable. So the TER covers the team's evaluation of Honeywell's risk analysis for tornado and seismic events. So basically the team looked at Honeywell's definitions of likelihood and consequence and found that they're appropriate for using the risk matrix to demonstrate risk levels. The team looked at likelihood as a combination that the event occurs, that material would be released, and that controls would fail. And it looked at consequences in terms of potential releases of uranium hexafluoride using standards set by EPA. So during our review, we looked at combinations of consequences and likelihood for various scenarios, and we found the risk levels to be low. So the TER covers the evaluation of the design of the structure, systems, and components. And this evaluation is used in evaluating the likelihood portion of the risk determination. The staff evaluated Honeywell's assessment of the seismic hazards and the structural modifications. So the team looked at the information that Honeywell provided on the seismic hazards and found it was complete and consistent with NRC's understanding of the seismic activity in the region. Thus, the seismic hazard assessment was found to be adequate for the design of the modifications. So the team looked at the engineering analysis supporting the modifications and found that the modifications for the building will withstand the design basis earthquake and will actually perform up to seismic loads equivalent to a 1700-year return frequency earthquake. And the team also looked at the engineering analysis for internal components and found that the modified restraints for equipment and piping are designed to withstand seismic loads equivalent to a 1300-year return period. We also looked at the analysis of the tornado's missile modifications, and again, the team looked at the information that Honeywell provided, and we found that Honeywell's assessment was consistent with NRC guidance on tornado strike likelihood and impacts. We found that design information was complete and that the modifications will shield areas with large inventories of hazardous materials. The team also looked at evaluating chemical consequences. The staff performed modeling to independently understand the release scenarios and to better understand the nature of the releases. The team found that the structural performance of the modified building and equipment will prevent releases from seismic and tornado missile events, and that severe earthquakes may cause releases, however, the likelihood is sufficiently low to demonstrate acceptable risk. So in summary, the TER stands as the team's record of their activities and their findings regarding the seismic and tornado modifications. And basically, the key findings we had was that the modifications are appropriately designed and will perform beyond the design basis. The modifications will prevent releases as a result of seismic and tornado missile events, and the modifications are protective of the health and safety of workers and the public. So that completes my presentation. I'll turn it over to you, Matt.
Again, my name is Mike Norris. I'm with the Office of Nuclear Security and Incident Response up at NRC headquarters. I'm a team leader of a team that does emergency plan licensing for nuclear power reactors and fuel facilities. So we do a little bit of both. Next slide. Basically, the regulations require that Honeywell has an emergency plan that for responding to radiological hazards from a release of source material and any chemicals that are associated with that. And also, it requires that the emergency plan identifies all of the types of accidents for which protective actions are required. Next slide. Prior to the facility upgrade, just one thing, in case some people don't know, Honeywell renews their license on basically a 10-year cycle, which we review their emergency plan as part of that relicensing. The emergency plan prior to the facility upgrade did not identify an accident sequence that would, occur due to a credible seismic and tornado event. So there was a missing piece of that emergency plan. And, they could theoretically have had a large uranium hexafluoride release. So that was prior to the facility upgrade. Next slide. As part of the review, we looked at technical evaluation reports because we're emergency planning people, not structural. And we relied on that to, give us the confidence that the facility structure, supports, and everything was upgraded so that, it would prevent and mitigate the possible releases. And also the implementation of the seismic safety systems and tornado shielding, also increased the protection for liquid uranium hexafluoride and total release. So we relied on the technical evaluation report for this. Next slide. And basically our evaluation was due to the improvements, we judged that the processes in the materials feed building were fully capable of withstanding the design basis seismic and tornado missile threats. And then we verified that corrective actions would adequately prevent, occurrence of a large UF6 release. Next slide. And then the emergency plan we verified it was revised to include a design basis seismic event and a tornado event also. And that's pretty much what we looked at. Again, we judged most of our input on the new Reg 1520 guidance document, as we had talked about, and engineering analysis of the upgrades. That's all I have.
Okay, my name is Jim Hickey, and I'm the branch chief of the inspection branch, which is run out of Atlanta. And what we do is we take all of the inputs from the analysis and evaluation, and we verify that that's translated into the modifications in the field, the procedures for the people that use that Honeywell, and also for the operators and how they do their job. First thing I want to talk about is something that we call commercial grade dedication. And commercial grade dedication is where equipment is determined to meet very specific performance criteria to support an important function. You can imagine a big plant. Not everything is absolutely critical to safety. There are some things that are lower priority and some things that are very important. And there might be a situation where, let's say, a valve needs to be replaced and the valve is obsolete. The manufacturer doesn't make it anymore. But that valve has to meet a certain quality requirements in order to perform its safety function. So Honeywell will look for an equivalent valve and do an evaluation to show that the critical needs that need to be performed for that particular component will occur at the same quality level, the same reliability level as that original component. And it's the commercial grade dedication process that ensures that. So we inspected how Honeywell used commercial grade dedication, the process, and we inspected specific examples of how commercial grade dedication was used. Something else we looked at was the seismic and tornado modification for the feed materials building, which is the major building that houses the chemical process. For example, there were approximately 1,500 rivets that were replaced with bolts to improve the strength of the connection of the structure of the building. And we inspected the installation of the bolts. We inspected the receipt, the inspection of the bolts themselves, the testing of the strength of those bolts. We observed the condition of the bolts in the field, the control and use of the torque wrenches used to make sure that the bolts were properly installed. So, and what that bolting did was improve the strength of the connection of the support structure of the building to ensure that it would withstand the analyzed seismic event. We also inspected building structural modifications that include additional supports and bracing. Additional beams were installed in the beginning. If you were watching the pictures as they were flipping through, you saw many structural changes to the main building. We inspected all the way from the analysis through the design to what ended up in the plant. The analysis said, this is the stress or how much force the building was expected to be subjected to in a seismic event. Then the design says in order to successfully withstand that, you've got to have steel that's a certain strength. It's got to be so wide or so thick, and that's all called out in the design. Then the design actually gets to cutting the steel and putting it in the field. We started at the very beginning of the analysis and went all the way down into the plant to verify the continuity of that process to ensure that what's in the field is going to support the analysis for the seismic event or tornado missiles. We also inspected the placement of we call tornado missile protection. In a tornado, things are going to get caught up in the tornado and fly around. Large pieces of debris, and there was an installation of shields in particular areas of the building to ensure that if a missile hit the side of the building, the shield is there to protect the important equipment on the other side of that barrier, and that barrier is going to be able to withstand the impact of that missile and not impact the equipment on the other side. Next slide. The installation of equipment, piping, and supports. So that covered the building itself and the changes that were made to the building. Now we go inside the building to the actual plant itself, where all the chemical processes take place. And we inspected the installation of numerous hangers and seismic restraints in the uranium hexafluoride process piping, tanks, and vessels. And we verified that the condition of the plant was consistent with the design. If there was a deviation, sometimes the engineers say this is the way it needs to be, and the workers get out in the field trying to follow the plans, and there's an obstruction or something in the way that it can't be exactly like what the engineer had envisioned. So they've got to do a little field change in order for the component to be installed. And we looked at those changes. So the design change, was the change acceptable? Is it still meeting the needs of the design? There was also a new seismic shutdown system. Now this is a system that in the event of an earthquake, it will actuate, it will stop the chemical process and isolate portions of the chemical process in order to limit any potential release in the unlikely event that there was a breach. So instead of a large volume of chemical liquid being released, it will be a much smaller volume. And the system is actuated by a series of sensors that are located on the ground at the facility. And if it reaches a certain shaking level, then automatically actuates without any operator action to shut down the system. Some of the new valves that are associated with that process are very heavy, about 200 pounds or so. So if you can imagine a 200-pound valve on a piece of piping, that valve is actually going to have supports all by itself to make sure that it doesn't adversely impact the piping. And we looked at the support structure for those heavy components. We observed the control functions and the features of the system, the proper operation of the system, and overall test of the system. We had inspectors in the control room, out at the seismic actuation station, and inside the feed material building when they did a demonstration of the system, and the system performed just as expected. Emergency preparedness exercise. Tony mentioned in his intro two things that we did. I'll talk a little bit more in detail. The emergency preparedness exercise. In one of the exercises, there was a simulated seismic event which resulted in a hydrogen fluoride release and a contaminated injured worker. We observed the Emergency Operations Center, its activation, how it functioned, incident command control point, and the conduct of personnel accountability. If you've got a seismic event, an earthquake, an emergency, the Honeywell folks, they want to account for all the workers that are at the facility. So they have to find each one of them in a timely manner to ensure that everybody's okay. In this particular scenario, someone was injured and they were contaminated. So they had to stand up the emergency response team, which we watched. They go out and do a search and rescue of the facility, find that individual, remove them from harm's way, do some decontamination of the individual, and also eventually isolate that hydrogen fluoride leak. All part of the scenario, the practice of their response in the unlikely event of a seismic issue. We also did a tabletop. Now, a tabletop was conducted kind of like this at a big conference table. And the tabletop had the representatives from the state of Illinois, local off-site support participants, and ourselves, the NRC, participated in the tabletop. And the purpose of the tabletop was to demonstrate the ability to coordinate between all these different entities, off-site, on-site, local, state, federal, all the different players